Welcome. Today we shall be discussing binary neutron stars, two neutron stars going around a common center of mass. We shall also discuss how these exotic systems have been used to test various predictions of the general theory of relativity to unprecedented accuracies. Most of the stars we see in the sky are binary stars. Most of them are very wide binaries with orbital period of years, perhaps even centuries. But some of them are close binaries, close enough to interact with one another. And we want to discuss those binaries in this lecture. We shall begin our discussion with what is known as the Algol paradox. And this is the paradox. Algol is a well-known binary which consists of two stars, one with a mass of about 8 solar mass and one with a mass of approximately 20 solar mass. What is extraordinary is that the low mass star, which is the 8 solar mass star, which is a helium star, is extremely luminous and much more evolved than the more massive companion, which is an unevolved main sequence star. Now, this is very puzzling indeed. Now, if you want to be convinced as to why this is puzzling, let me recall for you. So here it is. The 8 solar mass star is highly evolved and the 20 solar mass star is not evolved. It's still on the main sequence. The reason why this is very perplexing is the following. We know from our discussion of stellar evolution that more massive stars evolve faster because their luminosity is proportional to m to the power 2.5 and their lifetime is proportional to the total energy the star has, which is mc squared, divided by the luminosity, which is the rate at which it is radiating energy every second. And that lifetime is inversely proportional to m to the power 2.5. Therefore, you would expect the more massive star to evolve faster. And that is why this is a puzzle. How come the less massive star is more evolved than the more massive star? This is known as the Algol paradox. It is the resolution of this paradox that gave a great impetus to research on binary evolution and also for the formation of neutron stars in binary systems. So I now want to take you through the basic principles of evolution of two massive stars in a close binary. Let us begin with the gravitational equipotentials of a binary. There is a star here and there is a star there, and these are the gravitational equipotentials which are known as the Roche equipotential because Mr. Roche presumably discussed this first at great length. So let us look at the general features of this. Close enough to this star, let's call it star 1, let's call this star 2, close enough to this star, the equipotentials are circles, or in 3 dimensions, they are spheres. That means every point on that circle is at the same gravitational potential. The same is true of equipotentials around the second star 2 over there. But now if you go to a large distance from the star, you encounter an equipotential curve where the two equipotentials touch one another at the point L1, which is known as the first Lagrangian point. The great mathematician Lagrange was the first to discuss these things, so these points are named after him. So please pay attention to this particular equipotential. what this means is the following. If I have a test particle at the point L1, then the gravitational potential acting on it due to star 1 is precisely equal to the gravitational potential acting on it due to the star 2. Therefore, there is a conflict of interest. The test particle doesn't know whether it should go around star 1 or star 2, and presumably it will go around both the stars. Now, if you go to a larger distance, what you find are the equipotentials that go around both the stars. This is exactly what you would find in a molecule like the hydrogen molecule. When the two hydrogen atoms are far apart, the electrons go around the individual nuclei, but when the two nuclei come close enough to form a bond, a molecular bond, then the electron will go around both the nuclei. You will have molecular orbitals. And what we have plotted are equipotentials at greater distances, and they show very strange behavior, which we shall not be concerned with. I want you to notice in passing that in addition to the point L1, there are four other points, L2, L3, L4, and L5. These are special points in a binary orbit, in a binary system. Just for your information, the James Webb Telescope, which will soon become operational in a few weeks' time, has been parked at this second Lagrangian point L2, where this would be the Earth and this would be the Sun. That is because at that point L2, it is shielded by direct sunlight, shielded from direct sunlight. So these are the gravitational equipotential of a binary system. Now we won't discuss this in great detail any further, but we shall concentrate on this particular equipotential which touches at the first Lagrangian point L1, and that is known as the Roche lobe. In other words, this equipotential, please remember, this is the projection of the equipotential in a particular plane. It's actually a three-dimensional surface. This is also a three-dimensional surface. These two have been given the name as Roche lobe. This is the Roche lobe around the binary companion. This is the Roche lobe around the primary star. Now, the size of the Roche lobe, or the radius of the Roche lobe, if you could approximate this by a sphere, which you can, then the radius of this Roche lobe, as well as the radius of the Roche lobe, individual Roche lobe, will depend on the masses of the two stars and also their physical separation. Now, the important thing for you to appreciate is that the star, either of the stars, cannot become larger than their Roche lobes, because that is explained over there. So this is the Roche lobe we are considering. Let us say this is the more massive star. It evolves, it becomes bigger and bigger and bigger, it becomes a giant, and then it will fill its Roche lobe. Now, if it were to evolve even further, then the size of the star would have to become bigger than the Roche lobe, and that is not allowed. At that point, what will happen is the mass from this star will flow through this inner Lagrangian point onto the companion star. So there is the concept of mass transfer. So when a star evolves and its size swells and it becomes a giant, it can fill its Roche lobe at some stage or another. At this stage, it will transfer mass to its companion. So this giant star will transfer mass through the inner Lagrangian point to the companion star. And since the two stars are going around a common center of mass, this infalling matter has a large amount of angular momentum. Therefore, it cannot radially fall onto the companion star. It will swirl around it and form an accretion disk, and perhaps eventually from the accretion disk, it will fall onto the companion star. We shall discuss that in considerable detail in a few minutes. Now, since this matter has angular momentum, this matter, which is flowing through the inner Lagrangian point, it will spiral in towards the companion, form an accretion disk in the equatorial plane. Now, this accretion disk is a common phenomenon around all binary objects. We shall be discussing accretion disk around a neutron star in a binary. Later on, we shall be discussing accretion disk around a black hole in a binary system. So the accretion disk arises because of large angular momentum of the infalling matter. So if the star becomes bigger and bigger and bigger, it's like squeezing a tube of toothpaste. The toothpaste will come out of the opening. So the mass from the star will be transferred to the companion star. So let us try to understand this from a more familiar picture, namely gravitational potential of a star 1 over r, the potential of the other star, which is 1 over r. So these are the equipotentials, and that is the Roche lobe that we are talking about. Now, the more massive star will evolve faster. Let us say this red star is the more massive star. It will evolve faster. When it becomes a giant and fills the Roche lobe, it will transfer mass to the companion, as I just said. In this figure, what will happen is that the star fills the gravitational potential and reaches a point where the gravitational pull due to the companion star is just as strong, and the matter will flow from star A to star B. Since the transferred mass has large angular momentum, it will spin up the companion. It's like if you have a ceiling fan, if I throw matter at it at an angle, it has angular momentum, and if this matter hits the blade of the ceiling fan, it will spin up the ceiling fan. So, when mass is transferred from one star to the other, the companion star will be spun up. That is a very important part of our lecture today and in the next lecture. Now let us be very specific and consider a massive binary. For the sake of this illustration, I shall consider a massive binary with masses 25 solar mass and 10 solar mass respectively. And these are the Roche lobes of the two stars. This figure and several figures like this I shall show are taken from papers by Professor van den Heuvel, who is the most distinguished stellar astrophysicist at the University of Amsterdam in the Netherlands. So now let us pick up the story. The more massive star is the 25 solar mass star. Therefore, it will evolve faster and it will fill the Roche lobe as is shown over there. At that point, it will transfer mass to the companion star. And as it transfers mass to the companion star, the more massive star will suddenly become the less massive star, and the less massive star will become the more massive star. In other words, the donor star, which was initially more massive, will become less massive, and the receptor star or the receiving star, which was initially less massive, will become the more massive star. Now, let us assume that no mass is lost from the system. In other words, it's like a tube of toothpaste, which is connected to another toothpaste tube, so it can only go from this tube to that tube. It is not leaving the system. And in physics, this is known as a conservative mass transfer. Now, I want you to do some very simple calculations, which are at the pre-university level. Therefore, I do expect you to be able to do these calculations and verify the statements that I am just about to make. When a more massive star, the 25 solar mass star, say, transfers mass to the less massive star, the 10 solar mass star, the orbit will shrink. The orbit will shrink. All you have to do is to use Kepler's laws and Newton's laws. Conversely, when the mass donor is the less massive star and the receiving star is the more massive star, then the orbit will expand. So I wanted to verify these two statements because these have very, very important astrophysical consequences to things that I shall say and perhaps not have time to say. Let me repeat once again. When the more massive star transfers mass to the less massive star, the orbit will shrink and the mass transfer will become faster and faster and faster as the orbit shrinks more and more and more and more. But when the mass donor is the less massive star, then the orbit will expand and the mass transfer will become less and less drastic and eventually cease. Now let's go back to our binary. We began with a 25 solar mass star and a 10 solar mass star. The 25 solar mass star has transferred all its hydrogen envelope to the companion star. So it is now only 8.5 solar mass, which is the mass of the helium core. Where do these numbers come from? From actual computer calculation of the stellar evolution of star 1. And the companion star, which initially had a mass of 10 solar mass, now will have a mass of 26.5 solar mass. The orbit has also shrunk. The period of the orbit has also shrunk. Now, let us see what happens. Once this becomes a less massive star, it will continue to transfer mass, and this time the orbit will expand because you are having mass transfer from the less massive star to the more massive star. Now we will have a very luminous helium star of 8.5 solar mass. So let me repeat in case it's confusing. You started out with a 25 solar mass star and a 10 solar mass star. The 25 solar mass star transfers mass till the two stars become of equal mass. But the primary star continues to transfer mass, but now the orbit, instead of shrinking, will expand because it's now the less massive star. Let this story continue till you have got rid of all the envelope, the entire hydrogen envelope, and you are left only with an extremely luminous helium core. Now this helium star will evolve very, very rapidly and soon explode, leaving behind a neutron star of the Chandrasekhar limiting mass. Therefore, the neutron star will have a mass of 1.4 solar mass. Now let's look at the first picture over there. What you have is a helium star of 8.5 solar mass and a companion star of 26.5 solar mass. These were precisely the masses of the two stars in the Algol paradox binary. The more evolved star was the less massive star, and the less evolved star was the more massive star. Now we understand how the Algol paradox has to be understood. It's a closed binary where the primary star first evolves, fills its Roche lobe, transfers mass to the companion, and all that is left is the highly luminous helium core of about 8 solar mass according to the calculation. Now the helium star, as I said, will quickly evolve and explode as a supernova, leaving behind a neutron star. So we have now formed a neutron star in a binary system, and our story just begins. Now we have to ask the following question. When the 8.5 solar mass helium star evolves and explodes as a supernova, leaving behind a neutron star, will it disrupt the binary? Will the binary become unbound? Now, when the more evolved star explodes, 8.5 solar mass, remember, all that is left of the 8.5 solar mass is 1.4 solar mass of neutron star. So 7.1 solar mass of material has been ejected with tremendous kinetic energy. The question is, will it disrupt the binary? So I'm going to give you another pre-university level problem for you to solve. Here you have a star of mass m1. Here you have a companion star of mass m2. It so happens, even though m1 is less than m2, m1 is the more evolved star because it became less massive by transferring all the hydrogen envelope to the companion star. Now this star, m1, explodes and ejects a mass delta m. And this ejected mass delta m now expands in a shell, in a spherical shell. This is the mass ejected delta m. In the case of 8.5 solar mass, delta m was 7.1 solar mass, and what is left over there, m1 minus delta m, is 1.4 solar mass. Now the question is, will this supernova explosion disrupt the binaries, and the neutron star will go in its own way, and the companion star will go in its own way in the opposite direction? Now, how do we answer that? So here is a simple problem for you, and I strongly recommend that you do this problem. It's a very simple pre-university level problem. Let us assume the mass loss is instantaneous. In other words, supernova explosion is more or less instantaneous. Let's also assume that it is spherically symmetric, namely no angular momentum is lost from the system. It is spherically symmetric. A real explosion may or may not be spherically symmetric, but you make this assumption that it is spherically symmetric. Now I want you to prove the following condition for the disruption of the binary. The binary will be disrupted if the mass ejected delta m is greater than half the total initial mass of the system. The initial masses were m1 and m2. Mass ejected is delta m. So for the binary to be disrupted, delta m must be greater than 1/2 of m1 plus m2. So let us look at the expression. So binary will be disrupted only if the mass ejected is greater than 1/2 of the total mass of the stars. Please verify this theorem. This should not take you more than about 10 minutes of thinking. The calculation itself is utterly simple. Therefore, the binary will not be disrupted during the first supernova explosion of the binary that I discussed, 25 solar mass, 10 solar mass. Why? Initial masses were, at the time the star evolves, is 8.5 solar mass plus 26.5 solar mass, which is 35 solar mass. That's the same as 25 plus 10 is 35 solar mass. So m1 plus m2 is 35 solar mass. Delta m is only 7 solar mass or 7.1 solar mass, because 8.5 was the solar mass was the mass of the helium star, and we are left with the stellar remnant of 1.4 solar mass, the neutron star. Therefore, the mass ejected is 7 solar mass. 7 solar mass is certainly less than half of 35 solar mass, and therefore the binary will not be disrupted during the first supernova explosion. So we will now have a very interesting binary. A binary now consisting of a newly born neutron star with a gaseous companion star. Now, the companion star is still in the main sequence. You notice that the companion star is well inside its Roche lobe. But there is a wind, stellar wind from the companion, just as there is a stellar wind from the sun, namely the solar wind. Now, this stellar wind will be captured by the gravity of the neutron star, and the neutron star will emit X-rays. We shall discuss that in a moment in a little more detail. So the neutron star will suddenly turn on as a powerful X-ray source. Where is the energy coming from? It is the mass from the companion star, the stellar wind material for the companion star, raining on the neutron star. Now, eventually, the companion star will become a giant, fill the Roche lobe, and transfer matter at a terrific rate onto the neutron star. Now, this matter will spiral in and form an accretion disk around the neutron star, from which it will fall onto the neutron star. And because the incoming matter has a very large angular momentum, remember the angular momentum is proportional to the lever arm. The lever arm in this case is the distance between the two stars. And this angular momentum will spin up the neutron star. And that is the story that will be the nucleus of the next lecture. Now, because the more massive star is transferring mass, 26 solar mass as opposed to 1.4 solar mass, the orbit will shrink, leading to a runaway mass transfer in a very short thermal timescale. And there will be heavy accretion onto the neutron star, and the neutron star will be spun up due to the angular momentum it accretes from the accreting matter. Now, why does an accreting neutron star emit X-rays? When a test particle of, say, mass m, say an electron, falls on a neutron star, the gravitational potential energy release is roughly 10% of its rest mass energy. Where does this come from? The gravitational potential energy of mass small m is gmm divided by r, where capital M is the mass of the neutron star and r is the radius of the neutron star, roughly 10 kilometers in size. Now, if you put in the numbers here, please convince yourself that the value of this potential energy is approximately 10% of mc squared. mc squared being the rest mass energy of the electron or proton or a billiard ball or a mountain that is falling on to a neutron star. It's an enormous amount of energy. Now, let us consider an electron. The rest mass of the electron is 500,000 electron volt or 500 kilo electron volt. Therefore, 10% of that will be 50 kilo electron volt. 50,000 electron volt is in the X-ray region of the electromagnetic spectrum. Therefore, when matter rains on a neutron star, protons and electrons and ions fall freely onto the neutron star, they will emit X-rays. How are these X-rays emitted? Two things. During the infall, the electrons and protons will collide against each other and emit Bremsstrahlung radiation that we discussed in an earlier lecture. Then finally, the matter will hit the surface of the neutron star and heat up the patch of the surface of the neutron star to a temperature of the order of a few million degrees. And a hot plate of a few million degrees will emit X-rays. So when matter rains on a neutron star, X-ray emission arises due to two processes. One is collision between the electrons and protons as they fall onto the surface of the neutron star. And the second is they heat up the surface of the neutron star. The kinetic energy is converted to heat energy, and that hot plate radiates X-rays. So now let us discuss for a few minutes such accreting neutron stars in a binary system. As I already alluded, they will emit X-rays. And these are known as X-ray binaries. Now, X-ray binaries were anticipated long before the discovery of neutron stars. In 1962, many years before neutron stars were discovered, the great physicist Zeldovich in Moscow pointed out that if matter accretes onto the neutron star, the gravitational potential energy release will result in X-ray emission. This was an extraordinary statement to make when neutron stars had not yet been discovered. Now, in 1962, soon after this prediction was made, an extremely powerful celestial X-ray source was discovered, quite serendipitously, by a suborbital rocket. It was in the constellation Scorpio, and it was named as Scorpio X1, the first X-ray source in the constellation Scorpio. Within a year, the binary nature of this X-ray source was established. And after the discovery of pulsars by Jocelyn Bell in 1967-68, it became clear that SCO X1 was a neutron star accreting matter from the companion star. Exactly as Zeldovich had predicted long before the discovery of SCO X1. Today, many hundreds of such X-ray binaries have been discovered in our galaxy and in external galaxies by the Chandra X-ray Observatory. Now, here is a picture to summarize what I said as to how X-rays originate. Here is a normal star. It has filled its Roche lobe and matter is flowing towards the neutron star. It forms an accretion disk around the neutron star. And because the accreting matter is ionized and therefore charged, it is captured by the magnetic field lines of the neutron star and it forms a magnetosphere. And these charges can flow along the magnetic field lines and therefore they can flow on to the magnetic cap, polar cap of the neutron star, emitting X-rays. Please don't get confused with the neutron stars that Jocelyn Bell discovered. In that case, there was no companion. There was no accretion disk around the neutron star. It was an isolated neutron star that produced particles because of the electric field it generated by virtue of rapid spin and strong magnetic field, a la Faraday's unipolar inductor. Those are rotation-powered neutron stars. The energy, the action is due to the rotation of the neutron star. Here, so far, I have not invoked the rotation of the neutron star. The action is due to the matter accreting onto the neutron star. The end result is the same thing. It produces X-rays, and if this magnetic axis is not aligned with the rotation axis, the X-rays will be pulsed for the same reason that the radio radiation from pulsars is pulsed. So these X-ray binaries are most often pulsed X-rays. This, let me repeat once again, this X-ray emission is very different from the X-ray emission from the Crab pulsar, which is due to rotation of the neutron star. Now, there are two kinds of X-ray binaries. There are massive X-ray binaries where the companion of the neutron star is a massive star, like the one we discussed in our illustration. The companion of the neutron star was a 26 solar mass main sequence star. But you can also have a situation where the companion of the neutron star is only of the order of a solar mass or even less than a solar mass. So the mass donor is a less massive star, and those are known as low mass X-ray binaries. We shall, in the next lecture, consider the properties of neutron stars that are spun up in massive X-ray binaries, and in a later lecture, we shall discuss the properties of neutron stars which have been spun up due to mass transfer and accretion of angular momentum in low mass X-ray binaries. Those will be the millisecond pulsars. Now, let us continue with our story. We have got this far we had got to the stage where a neutron star had just been formed, and there was a companion star which was of 26.5 solar mass. Now the companion star will evolve. It will transfer mass to the neutron star, mass and angular momentum to the neutron star, but most of the mass will escape the system because the neutron star cannot accept more matter than a certain limit, which we shall discuss in the next lecture. So with the end result, you will end up with a neutron star whose companion is now an 8.8 solar mass helium star. Now that helium star will also evolve very, very rapidly, explode as a supernova and leave behind a neutron star. So you will have a second neutron star in the system. The first born neutron star was the remnant of the first supernova explosion. The second born neutron star is the remnant of the second supernova explosion. But the second supernova explosion will almost certainly disrupt the binary. Just look at it. The total mass of the system is 1.4 plus 8.8, which is 10.2 solar mass. What is ejected is 7 solar mass. So 7 solar mass is more than half of 10 solar mass. And therefore, our theorem, if the mass ejected delta m is greater than 1/2 of m1 plus m2, the binary will be disrupted. So the binary consisting of 2 neutron stars will be disrupted by the very explosion that gave birth to the second neutron star. So you will have 2 neutron stars flying away from each other with velocity vectors which are in opposite direction. But in very rare circumstance, the 2 neutron stars will remain bound. There has to be a conspiracy to bind these 2 neutron stars. And the conspiracy has to be one of the assumptions that we made is no longer valid. The 2 assumptions we made was that the explosion is instantaneous, which is a reasonable assumption. The second assumption we made is that the explosion is spherically symmetric. There is no loss of angular momentum. A supernova explosion need not be spherically symmetric, as is now becoming clearer and clearer, because we find neutron stars moving in the galaxy with tremendous velocities. This must be velocity it acquired at birth. That means that the supernova explosion gave it a kick, which in turn means that the supernova explosion was not spherically symmetric, but was highly asymmetric. It is this asymmetry that you have to invoke to produce a bound system of 2 neutron stars going around a common center of mass. But that is not the usual thing that you would expect. Usually you would expect 2 runaway neutron stars from a massive binary. The second supernova explosion will most likely disrupt the binary. Only in rare cases, the binary will remain intact. So let us summarize rather quickly the story that I have told you, which is really some 30 years of very hard work by very smart people in several groups, in several countries. We started out with a massive binary with a main sequence mass of 25 solar mass and 10 solar mass. The more massive star evolved faster, transferred mass to the less massive star, and the end result was the formation of the first neutron star in a binary. The first born neutron star accretes matter from the stellar wind of the companion and turns on as an X-ray source. When the companion star fills its Roche lobe and transfers mass, there will be heavy accretion onto the neutron star. The neutron star will be spun up because it's accreting not only mass but angular momentum. And then the second star will also end its life in a supernova explosion, which will result in the birth of a second neutron star. We will end up with either a double neutron star system or 2 runaway neutron stars. So that's the summary of what I have said in the last 15 or 20 minutes. So in rare cases, you will have a bound binary. That's just to repeat what I said. Now, the extraordinary thing is such double neutron star systems have been found by astronomers. And I want to discuss two of them. As to the details of their characteristics, we shall discuss that in the next lecture. The first binary pulsar system to be discovered was discovered in 1974 by Joseph Taylor and his student Hulse. Now, many years later, 20 years later, or 1993, they were awarded the Nobel Prize for Physics for this discovery of this extraordinary binary system. Now, this is what the binary system consisted of. It consisted of two neutron stars. One of the neutron stars was functioning as a pulsar. We know that because the pulsar beam is pointing towards us, and we can detect the pulsation from this pulsar. The second neutron star, we know that it is a neutron star for reasons that I shall mention presently, but it is not pulsating. Therefore, we can safely assume that that too is functioning as a pulsar. There is no reason why it should not, but that the pulsar beam is pointing somewhere else. So some astronomer in some other part of the galaxy will see this pulsar but won't see this pulsar. So we have a double neutron star system with one of them pulsating in our direction. Now this pulsar emits pulses, tick, tick, tick. So you can measure the period of the pulsation. Now, if this pulsar was absolutely stationary, then the pulse period will remain the same. But because it's a binary, it is going around the common center of mass, there will be a Doppler shift of the pulse period. Okay? There will be blue shift and red shift. And that's what is plotted here. What is plotted here is the radial velocity along the y-axis and the phase of the binary along the x-axis. In other words, the radial velocity is changing in this direction. Now, if this was a circular binary, then the modulation of the radial velocity, you determine the radial velocity from the Doppler shift of the pulse period. Okay? That variation will be sinusoidal. In circular motion corresponds to two linear harmonic motions, 90 degrees with respect to one another. So this curve will be sinusoidal. Now this curve is clearly not sinusoidal, it has very rich harmonics present. That is a signature of highly eccentric orbit. Therefore, we know that the orbits of these neutron stars are highly eccentric. They are not circular at all. Now, everything you want to know about this binary system was deduced by radio astronomers. This is the neutron star that we see. This is the neutron star that we don't see. The period of pulsation of this neutron star is 59 milliseconds. It's a very fast, it is the second fastest spinning pulsar after the Crab pulsar. Its mass is 1.44 solar mass. It is the first neutron star for which mass was determined to several decimal places accuracy. The companion is also a neutron star whose mass is 1.4 solar mass. That is very gratifying because according to our stellar evolution arguments, the neutron star must have the Chandrasekhar limiting mass of white dwarfs. The orbital period of this binary is 7.8 hours and the eccentricity is very large, 0.6. Now, I have to make a remark in passing. In Kepler problem, let us say the Earth going around the Sun, we can determine the mass of the Sun, but we cannot determine the mass of the Earth from its period. So how did they determine the masses of both the stars? There are several complications. When you see a binary, you know it's a binary because of the modulation of the radial velocity deduced from Doppler shift of the pulse period. But you don't know the inclination of the orbit. The orbit could be like this, it could be like this, or it could be like this. So when you try to set up the Kepler equations, you will find the sign of the angle of inclination of the orbit comes in, and you don't know what that angle of inclination is. This makes it difficult to solve for all the parameters of the system. But it so happens that when you have two stars, each with a mass in excess of the mass of the Sun, and the distance between them is only roughly 1,000,000 kilometers. So you have two neutron stars just 1,000,000 kilometers apart going around a common center of mass. This system is surely not describable by Newtonian gravity. You have to describe this in general relativity. So there are various relativistic equations that one can write down. And therefore, the number of unknowns number of equations becomes larger than the number of unknowns that you are trying to solve for. And it is because of that redundancy you are able to solve for the mass of the companion star. If you understood, fine. Otherwise, you might like to think about it, or you might just like to move on. So I want you to appreciate that this Hulse-Taylor system is a double neutron star system in a very tight and highly eccentric binary orbit with an orbital period of only 7.8 hours. Now this pulsar's name is 1913 plus 16. These are the coordinates of the pulsar in the sky, which you need not bother about. The period of rotation of the neutron star is 59 milliseconds. The period derivative is very, very small, 10 to the power minus 18 seconds per second. For the Crab pulsar, it was 10 to the power minus 14 seconds per second. The magnetic field is very, very low. It's only 10 to the power 10 Gauss. The magnetic field of the Crab pulsar was 5 times 10 to the power 12 Gauss. Most of them have magnetic fields of the order of 10 to the power 13 Gauss. The distance of the pulsar from us is about 7,000 parsecs. The orbital period is 7 hours 45 minutes, and the eccentricity is 0.6 seconds. Now, that was in 1974, and the Nobel Prize was given in 1993. And the reason why the Nobel Prize was given, I shall explain in a few minutes. Many, many years later, around the year 2000, a second double neutron star system was found. This time, the orbital period was only 2.4 hours. It was an even tighter binary. And this time, both the neutron stars are beaming towards us. Okay, so it's a double pulsar. It's not only a double neutron star system, but it's a double pulsar system. And all the properties of this pulsar have been determined, and we shall speak more about this in the next lecture, and therefore let me now go on to discuss how these two binary neutron star systems have been used to test general relativity to unprecedented accuracy. Up to now, many of the tests of general relativity have been done using the solar system. And the general relativistic correction to Newtonian predictions is extremely small. But in the case of two neutron stars going around each other in such tight orbits, of 7 hours and 2 hours orbital period, you would expect gravity to be much stronger and therefore general relativistic effects to be much more pronounced. And therefore it should be possible to verify the predictions of general relativity to far greater accuracy. And this has been done. So let's skip that. First, I want to introduce you to the notion of effective potential in Newtonian theory. I already discussed this when we discussed black holes and orbits of particles around black holes. But let me quickly repeat it. In Newtonian theory, the effective potential is given by minus gm over r squared plus L squared by 2mr squared, where L is the angular momentum. So if I add the two, I get the effective potential, and the effective potential is the curve with a minimum that I am now showing with my cursor. We already discussed this before, so let me go fast. So here is the effective potential plotted again in the right. So a particle, if it were at the minimum of the effective potential, it has only azimuthal motion. That will be a circular orbit around the central star. But a particle can also execute simple harmonic motion about this equilibrium position, as shown by the green double arrow over there. That corresponds to a radial motion. So a particle is going around not only in a circular orbit, but it's also executing radial motion. The frequency of the circular motion is same as the frequency of the radial oscillation, and that results in closed elliptical orbits. These are the Kepler ellipses. Now, in general, so to repeat in words, the in and out motion superimposed on the circular motion produces the elliptical orbit. These are the Kepler ellipses. Now, it is an accident of 1 over r squared potential. It's an accident of 1 over r squared potential that the period of the in-out motion is the same as the period of the circular motion. And that is why the ellipse is closed. Okay? It's an accident of 1 over r squared potential. But there's no guarantee that the potential will be 1 over r squared. In general relativity, it is not 1 over r squared. So that's the point I'm trying to make it. Therefore, it is this coincidence that produces the Kepler ellipse, closed Kepler ellipse. Coincidence being the period of the radial oscillation is the same as the period of the circular motion. Now, in Einstein's theory, the effective potential has a maximum. The effective potential has a maximum. Secondly, the effective potential has a 1 over r cubed term. You notice there are two terms here. There is 1 over r here, 1 over r squared here. So if I multiply the two, I have 1 over r cubed. Therefore, this effective potential of Einstein, excuse me, these are various plots of a different angular momentum. Same here in Newtonian theory. These are for various different angular momenta, which we discussed in the case of orbits around black hole. But just concentrate on this one that I'm pointing to. Now, this has a 1 over r cubed feature built into it in addition to 1 over r squared feature. The net result is that the period of the in and out motion in Einstein's effective potential is not equal to the period of the circular motion, because this effective potential is asymmetric and it has a 1 over r cubed term in addition to 1 over r squared term. This means the ellipses will not be closed, which means the ellipses will precess. Okay? It is simple to show that this will give you the precession of the perihelion of Mercury. So this is the plot that I already showed you. So all I'm saying is, here is Einstein's effective potential, and this motion, this radial motion, combined with this circular azimuthal motion, gives me precessing elliptical orbits. We will not discuss all these other things. We discussed that already in the lecture on black hole, and that's not relevant for us. So all I want to say is that the orbits of planets in Einstein's theory of gravity are not closed ellipses, but they are precessing ellipses. So you take Mercury, for example. This is what the orbit of Mercury will look like. The perihelion of Mercury will change its location because the ellipse is precessing. Now, one knew that the orbit of Mercury precesses. It precesses madly. It precesses at the rate of 0.159 degrees per century, or 574 seconds of arc per century. It is a ever so tiny precession, but it is there. Now, I told you that orbits are closed ellipses in the Kepler problem. Why is the orbit of Mercury precessing? That is because in the Kepler problem is a two-body problem, but we have these other 8 planets in the solar system. So there's a perturbation of the orbit of Mercury due to the presence of other planets, and that is what causes precession in Newtonian theory. And that precession is very large, but what was puzzling was that astronomers could only account for 531 arc seconds out of 574 arc seconds due to these many body effects. So there was 43 seconds of arc of precession per century that was left unaccounted for. And this is what Einstein tried to explain using his new theory of gravity. And in the paper that he published on the 25th of November 1915, he estimated that this precession due to general relativity should be of the order of 45 plus or minus a couple of arc seconds per century. So Einstein sent a postcard to one of his friends saying, "For a few days I was beside myself with joyous excitement. The discovery has given me palpitations of the heart. I had a feeling that something actually snapped in me." To him, this was a tremendous triumph of his new theory of gravity. Now, the rate of precession of the semi-major axis of the Hulse-Taylor binary pulsar is 4.2 degrees per year, not 43 seconds of arc per 100 years, but it is 4.2 degrees per year. So you can see how dramatically large general relativistic effects are for this double neutron star system. So here is a little table. The precession of Mercury is 0.00159 degrees per year. The Hulse-Taylor binary pulsar is 4.2 degrees per year. And for the double pulsar, fasten your seatbelts, it is 17 degrees per year. So within your lifetime, that ellipse will precess one full round. Extraordinary. So you see how strong general relativity is for the double pulsar system and even for the Hulse-Taylor pulsar system. Now you can compare these numbers with what the theory predicts, and people have calculated, and it turns out that these amount to verifications of general relativity to a fraction of a percent accuracy. I shall show you a table. The next result is what is known as Shapiro time delay. So here is the Sun, here is the Earth, here is Mercury or Venus, one of the inner planets. So what radio astronomers did was to send a signal using a radar and bounced it off the surface of Mercury or Venus. And what you measure is the time delay between when you send the pulse and when you get back the pulse. So that time delay, the function, is like this as the planet goes in the vicinity of the sun. So the time delay changes for various reasons. Now you can ask, what will be the extra time delay due to general relativity? Why should be an extra time delay? That is because in the vicinity of the sun, space is curved. And since you are looking at grazing angle, the planet is over there, the light ray goes through curved space-time in the vicinity of the sun. There, its trajectory is not a straight line, but it's a geodesic. So it takes longer. And therefore, the time taken to go from the Earth to Venus and back, or from the Earth to Mercury and back, will not be just the free travel time at the speed of light, because in a sense, light is slowed down in the vicinity of the sun, and that is what is known as Shapiro delay. So, light travels slower in a gravitational field. C is 1, the dr by dt is c into 1 minus 2 gm by rc square. Therefore, when r is close to the sun, then you find there is a significant slowing down of light, as seen by a distant observer. A local observer will always see light traveling at the speed of light. Now that is the prediction by the general theory of relativity of the time delay. Time delay will be maximum when it is close to the sun, but unfortunately the planet will be eclipsed when it is really on the other side of the sun. Therefore, what you can measure is this blue curve up to the eclipse, and this blue curve after the egress from the eclipse. So this is the Shapiro time delay experiment. So what does the experiment tell us? The time delay due to the curvature of space was first measured by Shapiro, sorry for the mistake there, that should be O, by bouncing off radar signals of the surface of Mercury and Venus when it's very close to the sun. The ratio of the measured delay to the delay predicted by general relativity is 0.9 plus or minus 0.2. So ideally it should be 1.0. So it is 0.9 plus or minus 0.2. Pretty good, right? But the same Shapiro delay has now been measured with a double pulsar, because the pulse from one pulsar, as it travels towards us, comes in the vicinity of the other neutron star, and there it is slowed down. And this is the Shapiro delay, the black error bars, that is the observational data. The red curve is what the general theory of relativity predicts. So the ratio of the observed to the predicted is now 1.009 with an error of 5 in the fourth and fifth decimal place. So the measured delay by predicted delay using the double pulsar is 1.009 with an error of 55 over there. So this is a spectacular verification of the time delay prediction by general relativity using the double neutron star system. So I won't bore you with all this table, but let me quickly summarize. With the Hulse-Taylor double neutron star system, where you see only one pulsar, that is the 7.8-hour binary, the various predictions of general relativity, I've just given one or two, precession of the periastron of the orbit and the Shapiro delay. Various predictions have been measured, and the predictions have been verified to a level of 0.2%. Pretty good. Now, using the double pulsar, all these predictions have been verified to the level of 0.05%. So that's spectacular success in verifying the predictions of general relativity using the double neutron star double pulsar system. The final thing is the shrinking of the orbit of the pulsar. When two masses go around each other, they emit gravitational radiation. We shall discuss that in a subsequent lecture. The energy and angular momentum carried away by the gravitational waves has to come at the expense of the orbital energy and the orbital angular momentum. Therefore, just as an electron going around in a circle, as it radiates, will spiral in, so similarly, a planet going around a star, as it radiates gravitational waves, its orbit will shrink, it will spiral in. The rate of change of semi-major axis is given by the total energy is 1/2 g m1 m2 by the semi-major axis. Remember, this comes from virial theorem. If you recall from our first lecture, the total energy is 1/2 of the gravitational potential energy. The gravitational potential energy is g_mm divided by r. Therefore, the total energy according to virial theorem is 1/2 of g_mm over r. Now, I can take the derivative of this and I get dA by dt, that is the rate of change of the semi-major axis of the ellipse because of the emission of gravitational radiation is given by this expression. And the right-hand side, dE by dt is the energy radiated per unit time in the form of gravitational waves. Now, general relativity gives this following formula for the luminosity or the energy radiated per unit time in gravitational waves. Don't worry about the formula. I only want you to know that general relativity gives you a precise formula for the energy radiated by a pulsar as it goes around the common center of mass, with the semi-major axis being A. Now, a to the power 5 comes in the denominator. So I substitute this formula into that formula, and I get dA by dt is proportional to 1 over a cube, where a is the semi-major axis of the ellipse. Therefore, as the semi-major axis shrinks from Kepler's laws, its orbital period will change. Now, here is the change in the orbital period of the Hulse-Taylor binary pulsar as a function of time from 1974, when it was discovered, to 2008 or 2009. If there was no gravitational waves, the orbital period will be constant, that horizontal line. The solid curve curving downwards is the prediction of the change in the orbital period in general relativity due to the emission of gravitational radiation. And the dots are the experimental points. And that is why Hulse and Taylor were given the Nobel Prize for Physics for this discovery, which was the first demonstration of the existence of gravitational radiation. Yes, we didn't detect directly the gravitational waves themselves. That had to wait till 2015. But this was sure evidence of the existence of gravitational radiation. So the observed change in the orbital period divided by the predicted orbital period was 0.997 plus or minus 0.002. Spectacular confirmation of general relativity. Now, it is stunning to know that the orbit of the binary pulsar is decreasing by 1 millimeter every year. So we can imagine over 10 to the power 8 years or 10 to the power 9 years, how much the orbit will shrink. For the double pulsar, the shrinking of the orbit is even more dramatic. It's almost 1 centimeter per day, 7 millimeters per day. Okay. Now, so these two neutron stars, as they go around the common center of mass, will emit gravitational radiation. Their orbit will shrink. The semi-major axis will decrease, and therefore they will radiate even faster, because in the formula, the rate of change of the semi-major axis, dA by dt, was inversely proportional to the third power of the semi-major axis, 1 over a cubed. Therefore, as a decreases, the orbit will shrink even faster and faster. So many millions of years later, the two neutron stars will spiral in and eventually coalesce. And just before they coalesce, they will emit a huge burst of gravitational waves. And it is those gravitational waves from two coalescing neutron stars that was discovered on the 17th of August in 2017. So two neutron stars, they didn't detect the gravitational waves at the time of the coalescence itself. That is because as the two neutron stars come closer and closer, they are coming in faster and faster and faster, and therefore the frequency of the gravitational waves will also be much higher. And LIGO, the laser interferometer, which was used to detect these gravitational waves, could not detect gravitational waves of those frequencies. But an upgrade of LIGO will be able to detect it. So next time, when they detect the coalescence of two neutron stars, they'll be able to watch the gravitational radiation right up to the coalescence and the formation of, we don't know what, perhaps a black hole. So this is the gravitational wave burst as the two neutron stars were just about to coalesce. So that is a brief glimpse of the exciting astrophysics and physics that can be done when you have a neutron star, let alone two neutron stars, in a binary system. In the next lecture, I want to discuss what I have called as the reincarnation of pulsars. Pulsars die a natural death when their periods lengthen beyond a certain critical period. So they're buried in the graveyard of neutron stars. Every now and then, one of those dead neutron stars, if it happens to be in a binary system, can be born again from the graveyard. It is these born again neutron stars that I want to discuss in the next lecture. And that's a very exciting story, and I hope you will look forward to it. Thank you very much for your attention.